Okay. It's a little disaster with you will come up. I was trying to hear what you were saying. I catch a little bit of. I wanted to correct you.
Well, it was mainly directed to you, but
you said recently he's been working at the edge of chaos. You mean for how many decades?
Used to be a very good friend of mine.
Used to be. That's fine.
But then we diverge. That happens. So, but I mean, independently of all that, I respect his work as a physicist. And I think it will be very useful for us, for all of us, to hear a little bit more about it.
Well, thank you very much, even if I still feel very warm
I'm sorry.
all the time. I don't know what you're talking about. Anyway, well, I have to thank Rafael for giving me a slot in your meeting. Thank you very much. I'm the last speaker of today. So if we think of, so if it was like a meal in a restaurant, you have had already the main courses. So all I have to, or I'll try to do is just to have a dessert. I don't think I'm in the mood to convert the dessert into a digestive, maybe, who knows. But anyway, let me begin and move along. When Rafael asked me to give a title, I was in a rush, and I just used the title of a previous talk. It's not exactly the same content, and I was not aware of the audience of this meeting, how interdisciplinary it is. It has a very heavy component in biology and life sciences, and it also has one component in complex systems that has to do with networks and maybe social networks, according to what I led the program. And but I left the title there, and the title is going to take me a little bit of time, not much, because I had to explain the title. So that was not a good. It's not a good title if I have to explain it. So first. You realize that there is something called a Feigenbaum point. You may think, well, who was or who is or where is Feigenbaum, and what is this point? And today I was just looking at the slides and realized that I had to say what is the Feigenbaum point. So I decided to place it. Oh, you can see it.
It's there, yeah.
It's here.
Yeah.
It's misplaced. It's not really well placed. So at least the point is there. Now I have to see. It's not one point. In this slide, there are an infinite number of Feigenbaum points. And it goes, it's a name for something that many of you know, that in these simple, classical, iterated, nonlinear maps that were studied with gusto in the 70s, in the 80s, these simple one-dimensional maps are dissipative. Because they are dissipative, they have attractors, and then there is this characteristic that was realized long ago, that for this type of simple maps, there are only three routes to chaos, and one, they are very famous for nonlinear dynamical people. They are also very well known, and one of them is the one that proceeds via period doubling. And the slide, you may recognize the picture here, is just the collection of attractors of a unimodal map. And the unimodal map that is most convenient to use is the so-called logistic map, which is just a single parabola. And then here you can see, well, I must say, I don't know why, here. Here the horizontal axis is to be the control parameter that is contained in this unimodal map, from a small value to large value. And here are the values of the positions that they are taken by the iterations. So this is, if you want to call it phase space, the y-axis, and here is the control parameter axis, and then there is one attractor per each value of the control parameter, and there is a special one which is just the accumulation point of these bifurcations, these forks. They all appear in a sequence, and the sequence has an accumulation point, and it's there. But if you had a better resolution of the picture, then you could see, well, this corresponds to period 1, period 2, period 4, period 2 to the n, and 2 to the infinity is the Feigenbaum point. So all these words just to begin with the title. And then one would say, oh, so the Feigenbaum point had an old phase. What is the old phase of the Feigenbaum point? Well, we'll see a little bit about that, but it's something that was a lot of work or many references in 25 years ago, 30 years ago, or even more. And many people work around it. Feigenbaum had a better job at sticking his name in there. And what I am going to tell you is that I've been working in this very old problem for already, not recently, a decade or more, and by circumstances, and I'm telling you, I really enjoy it. And I enjoy many things that come up in this problem, and actually many new things. And these new things are the new phases. And I may say there are about half a dozen new phases. But for this meeting, I chose 2 of these new phases because the program was one of them directed towards these life science systems and the other ones to networks. So anyway, if you had a very good resolution, very good eye, you could see that you also have little reproductions. Here in this window or this strip, you have 3 reproductions of this main period doubling cascade. And if you could be looking in more detail, you would see many more ones. So this Feigenbaum point, this accumulation point, repeats itself an infinite number of times there. Well, that is enough. So these are the two pieces I want to describe to you. I will get into the matter. It is like a dessert. It's not very heavily technical or anything. I hope so. And I will only read now the first part because that's what I'm going to talk next. And this is reproduced later on, so I only read the bold. So the first part is called a dynamical model for hierarchy and modular organization. And the second part has to do with a nonlinear viewpoint of complex networks. And about the first part, yes, I'll go through these things because it had a little story. I was recently, talking with top man in our complexity sciences institute, the C3 that you mentioned. And we had a lively conversation. The conversation was, these complex systems, you cannot use your traditional analytical methods. You cannot use all these things that they're not producing anything. You have to deal with each problem by itself. You cannot put them together in a general framework. You better learn about data mining and something like that. And I was impressed by that. And my reaction was, no way, it cannot be. Not because it would be actually true scientifically, because it would be leave me out of the game. I said, I'm not going to do data mining or something like that. So I went into, I did a Google search, and the first 4 lines had to do with the Google search. And then I found something. I just copied them. I didn't write them myself. I just copied them, cut and paste. It says, quest for a possible general explanation for hierarchical structures. So that page talked that there exists the quest for a possible general explanation. Good, copied it. Then I went into the next, found the next thing. It says, the generation of dynamical hierarchies from a formal system is not trivial. So, okay, we go into the next one. It says, genuine emergence is strongly associated with nonlinearity. So I copied it. And then finally I found a hierarchy of building blocks operating at the edge of chaos is a characteristic of complex systems. I said, okay, I finished my Google search. And then I wrote myself here. Can all of the above be obtained rigorously from a simple, iconic, iterated map, meaning the logistic map? And that's what we're going to talk about. So here is the structure of this simple non-linear game, iterated maps, in which you have a function, non-linear. It has a phase space variable. It could be a scalar, it could be whatever. And it has another variable, which is the control parameter, which again could be scalar, but could be anything. So, but we are here going to have only a little real interval and also 2 real intervals for the control parameter. And the game is played like this. From the very beginning, you have your function. You choose a value of the control parameter. You choose an initial value of the variable x, and just see the image. And repeat the procedure on and on and on. And that gives you a string of real numbers, a string of values, that we will call them the orbits or the trajectories. 1 per each initial condition x sub 0. And this produces a time series, a simple time series, that can be periodic, we say the orbit is periodic, or can be regular, non-periodic, and we say it's irregular, or we, after defining accompanying quantity, we could call it chaotic. Anyway, this is the game. It's as simple as that. And then we start, and this is for you, because this is making contact with some of the talks. So here you have a hierarchy that you recognize. Planta, Protista, Animalia, you must have seen this. I had another one which came from early Christianity, in which you had the God and the angels, and then all the way down to the purgatory somewhere, and then you can see many others. If everybody would be physicists here, we'll have this big bang just going on and on. And this you can see very quickly, and no point. This is just an illustration. And this is another illustration that I thought it was suitable for this occasion, in which you have, this picture. And then something more schematic, like we're talking about levels of a ladder structure, of a hierarchical structure, and we have modules, and they are somehow connected. And I don't really like the word emergent, but here it is several times, and it's important to mention that. And here we're back. So this is the collection of attractors of a unimodal map, a map that has only one hump. It could be the parabola. It is shown here, 2 typical forms of it. We have already talked about it. And that's what we're going to be using to see if these questions that I started with can be validated. So this cascade, period doubling cascade, which ends up at an accumulation point, which is the Feigenbaum point. I did not talk about the right-hand side of the figure. Here, for the maximum value of the control parameter, you have a completely irregular attractor, a chaotic attractor, so that if you start with an initial position and you iterate, then all subsequent positions in the orbit fill up little by little all of this band. So you have a chaotic band attractor, and if you reduce the control parameter in value, apart from these accidental periodic windows, you can see that the band shrinks, and at one point the band splits into two, and you continue with the shrinking, and the band splits into 4, and then into 8, and then into 2 to the end. And then you go through band splitting of chaotic attractors, and you go from period doubling of periodic attractors, and they join exactly at the same Feigenbaum point. Okay, so that cascade is shown here in logarithmic scales. It looks deformed. It's the same cascade. So here I have the positions in absolute value, because I'm using the interval -1 to 1. And I have here the cascade plotted in this particular way with respect to the value of the control parameter at the Feigenbaum point. And I look at it, and I'm not going to say much about it, it looks deformed. But I will say that this figure, there are some distances between positions called diameters, which are very important. Now I accompany this left panel by this other panel at the right, in which I do something very different. I fixed the control parameter value at the Feigenbaum point, at this value, and now I only look at one orbit, an orbit that starts at the origin, meaning at the position where the maximum of the map is. And I just look at that orbit, and here you can see the result. And you can see that half of the positions of the attractor are on the top band, because they're all the odd times, and the other half are down here because they're all the even times. And here you have 1/4 of all of them, and so on and so on. So you can entertain yourself very much with this plot. For example, you can take a subsequence of positions and see that they are aligned, and if they are aligned in logarithmic scales, that's the Pavlov reflex of any person practicing complex systems. It says plot log log, and it uses straight line, and it says power law, we are in business, and so on. So this plot I have here because this is the dynamics inside the attractor. My initial position was at the attractor, and every subsequent position has to be within the attractor. But there is another possibility, that my initial position is not the position of the attractor. So then I have an orbit, a trajectory, that moves and gets eventually close and then arrives at the attractor. So there are two types of dynamics: the dynamics inside the attractor, which is shown here, and the dynamics towards the attractor. And then we are going to wonder about that, because you may say, it is like the two sides of the moon, because we see only the dynamics inside the attractor. To see the other dynamics, we have to do something else, something different. And we'll get into that. But this slide is here because it points out everything here has to do with the way in which this problem was worked from the late 70s, 80s, 90s. Was moving the value of the control parameter and see what happens. But we have a different point of view, which is place yourself at the accumulation point, at the Feigenbaum point, and then only look at the dynamics there. And incredibly, both are related. As you can see, if you select points on one side or distances and so on. Okay, so
this corresponds to powers of 2 as well?
No.
Dispositions in
The problem has what's called discrete scale invariance, which means that there is similarity reproduced as powers of 2. Okay. It's important. It's power of no other powers but powers of 2. Then I may say this, but I may only see then the first part of the talk because I have a limited time. But I will say that in order to look about something that has to do with the life sciences, which is again non-serious what I'm going to say, it is that you can see this as the development of the period doubling cascade, as if it was a living being. It starts with period 1, you move along with control parameter, bifurcates into period 2, bifurcates into period 4, so it's growing up, it's getting of age, and then you have the accumulation point at the right hand side, which is at mu infinity, period 2 to the infinity, the last of the periodic orbits, not chaotic yet. And then you realize that the positions at mu infinity are the positions that were used in the development of the organism. And we have, I don't know whether it's general, but at least I remember it here in Mexico that you say, no, it's more general. It says that the moment in which you die, that instant, you recall all your life. So here death is the Feigenbaum point, and you recall, anyway. So now this is just going to be like, we're going to be for a while, for 10 or 15 minutes, we're going to be geographers. So we're only going to go and see what we find. And we're going to look at the dynamics towards the attractor, different attractors, and I am just looking at period 2 to begin with. Let's start it easy, period 2. And here is the map composed twice in red. But what is interesting is that what we did was to place an ensemble of initial conditions uniformly distributed in the phase space in the interval -1 to 1. We put many initial conditions uniformly distributed, and then we iterated the map, and we just wanted to see when did they arrive at the attractor. The attractor is made of 2 points, one at 0 and one at 1. And so it's not to look at this scale here, but this one, which is called the time of flight, how many iterations until you reach the attractor. And it's a cutoff in order not to have an infinite time. So you say it has arrived at the attractor if you are epsilon to the minus something. And then what you see is that there are 2 points. There is one point which takes an infinite number of steps. And that's because this is a repeller. It's the continuation of this solution that is not drawn here. And it has one pre-image, meaning if you iterate this position, it takes you here. And then you see the basic, you realize, then you get, since you're not getting much, you say, well, there should be something that get a little picky and says, we want to know which initial conditions arrive first at the position x equals 0. And then we want to see which initial conditions, which positions arrive first at the other position of the attractor, which is x equals 1. And then you realize that there are 2 basings of attraction. One is this one in the middle. All positions here arrive first at 0, and those here form the other basin. Very simple. Now you go into period 4. And here is just to remind you that you are there in the cascade, and you have the function iterated 4 times in red, and now you have 4 positions. The attractor has 4 positions, 2 around here and 2 around here, and you do the same calculation, and you look at the times of flight, how long it takes, and you see it gets really very complicated. Suddenly it becomes very complicated. And you see there is a lot of this long time positions, they seem to cluster around here where you had only one peak, and then you have also that. I said, oh, surprise. I said, let's just draw the same, this is the same figure as before, only that now this part is using two colors, orange and green, and green is everything that is to the left of this point, and orange to the left, to the right and to the left, and so that this is the position of the old repeller, the first repeller, the patriarch, because here when you go into period 4 you have another 2 repellers and so on, and then you use this logarithmic scale only in the horizontal axis, and then you realize that because of this even spacing that you have this exponential clustering of these little valleys. So that's why you see this, just you are looking. And then the 4 positions, which are these, the values of the 4 positions, of the little valleys, the little basins, we paint them different color according to which of the positions of the attractor are reached first. You first arrive at x equals 0, x equals 1, x equals 0.6, x equals minus 0.3, something. So you have 4 bases of attraction, and then you realize how they are distributed again in a logarithmic scale. And so you have this. What happens is that the boundaries of these bases of attraction have become fractal, and that's what you look at there. And I don't think I have another slide here, but suppose that now you place many initial positions, say at the bottom of these little valleys. I put one here, one here, one here, one here, one here, one in each, all of them. And then I iterate and I see what do they do. And what they do is that this one that was in red at the next iteration visits the next red little valley, and the next iteration the next red, and the greens go from green to green, and the black to black, and the blue to blue. And if it never ends, because I put as many as infinite number inside these clusters, and then you realize there is a very strict order in which trajectories flow towards the attractor. We're beginning to see. It has to do with this. You see this in the lore of this there is a lot of order in chaos, and here we have something which is just transient. It's going to be transient chaos. But let's go on, and then I go to period 8. Period 8. And I do the same thing, and I look at the times, and then I spent a lot of, how you call it? In the printer.
Ink.
No, toner. And you say, well, that's it. We're not going to do the next. We actually did more. And here's the same thing. You plot them. This is the same picture, but using again differentiated in colors according to what's at the right and the left of this, which is just the position of the first repeller that keeps advancing, and we use it as a boundary here. And then in logarithmic scale, you can see that now these clusters are equidistant, and so you realize what is happening. And what is happening is like this eventually. It is like if this talk had been very successful and the auditorium was completely full, it was everybody sitting, it is not a single empty seat, and he said, that's it, thank you very much, clap, clap, and Rafael says, now you can leave. And the only way to leave is that you stand up, and then you have red chairs, blue chairs, black chairs, and you can only go to the door according to the dynamics, whereas the others, alternating ones, go to the other side. It is like that. But once you are in the next period, and we have the room, then you have to do, before, you have to come down to the first row. And then when you go to the next period, then it's a theater. It has many floors. It's an infinite theater. And then you realize what happens at the Feigenbaum point. It's a building with infinite number of everything. And how do you empty it? Well, according to the rules that we as geographers were to find. Here is a bit of the same gaps that are formed. I'm not going to them, it's just sequential formation of gaps. If, black means that there were initial positions everywhere, and now gaps appear quickly in time, and we can describe them in more detail, but there's no point now. And then you can also do something more quantitative, which is, let's see, I put many initial positions in many little boxes, and say I put 10 positions per little box or something like that. So that is the numbers that are here. This is the number of boxes. This is the number of trajectories. This is the number of trajectories per box. And this W is the number of bins that is still occupied by trajectories at time t. And then you can see them here in black, again logarithmic scales for period 2. It just goes down exponentially. And then you can do it for period 4, as we have seen before, and it now has a little wiggle. And then you can do it for period 8, and it has 2 wiggles, and then you can do it for other periods, and then you can see that develops what are logarithmic oscillations. And you know that logarithmic oscillations are the fingerprints, is the fingerprint of discrete scale invariance, because the exponent in the power law is a complex number. And so what? Well, I just wanted to show it to you, but you can see the development of a power law in a world that is exponential, and that is the first little grasp of what we wanted to get as an answer to this colleague in the C3, that you have an emergent property out of a nonlinear system like this.
So what you're saying is that appearance of power laws, which is quite difficult, are based by simple exponential things that are arranged in sort of rapidly?
Well, I want to say the following. I want to say that a bit more than that. Let me just...
More than that?
Oh, much more. What I'd say is that you actually start from a single assumption, and that's a very simple nonlinear map. So the rules of the game are set up from the very beginning and are very succinct. Then what you do is something that has not been done before, which is to study in detail the dynamics towards the attractor at the Feigenbaum point. And then you realize that this dynamics is very complicated. In order to have a glimpse of how this dynamics is, you say, but let's look at period 2 and then period 4 and period 8, and let's then just extrapolate and see what's happening at the Feigenbaum point. And what you see is that the dynamics has a modular structure. This thing of getting out of a cluster of clusters to an order of fewer, one less cluster of clusters, from cluster of clusters to cluster to a single peak, to a single valley, to the position. So the flow of the ensemble of trajectories at the Feigenbaum point has a ladder structure, a hierarchical structure. You can see the modules by looking at these logarithmic oscillations. You can see by how many logarithmic oscillations have you traveled with, what have you actually done in this pre-image world, and then you realize that naturally they are getting time scale separation, because there goes these times. The time it takes to empty a given level of clusters is 2 to the n. And the time it takes to empty a cluster of a higher order building block is to the n, 2 to the n plus 1, and so on and so on. And so time scale is happening. You have life in one module or level. You have, but life, not dynamics, they are just flowing away. But they comply with all these things. And then you finally say, do I get something new at the end? And I just wanted to point first that as a candidate of new is this power law. Okay, but there is more, because we are interested in statistical mechanics. And then we started with a simple question, which was, you have two types of dynamics. Dynamics inside the attractor, very well understood, very interesting things that not today, not here. And you have dynamics towards the attractor. And because you are a serious person, you say, oh, they are different. Would they be related or not to each other? And you say, maybe they are not related. Maybe you have to study one, familiarize yourself with it, and then study the other one, and you don't find a relationship. And then it says, but what if the opposite? Maybe they are related. Let's find out the relationship. So we tried and found the relationship. Yes, they are related. And said, that's interesting. In which way are they related? And then it comes the biggest surprise that I'm just going to say with words, is that they are related in a statistical mechanical fashion. Meaning, I can write a typical statistical mechanical expression, which would be a partition function in the right-hand side. And that partition function is built up only of quantities of the dynamics inside the attractor. And then I look at the left-hand side, and I see that the left-hand side is something like the exponential of a thermodynamic potential, the exponential of free energy or an entropy. And then, what is it made of? It's made of that W of t. So you have an equation in which one side belongs to one dynamics, the other side belongs to the other dynamics, and the expression is statistical mechanical in nature. And then you say, what kind of statistical mechanics? This is, well, one that is a little bit weird, because it's not Boltzmann-like. What do you mean not Boltzmann-like? We don't know anything that's not Boltzmann-like. Well, let me tell you or remind you that the dynamics at the chaotic attractors has the two main ingredients of statistical mechanics, equilibrium statistical mechanics, which is ergodicity and mixing. But the dynamics at the Feigenbaum point has lost these two features. It has an infinite memory and is not mixing. It has vanishing Lyapunov exponent, so the two legs of statistical mechanics are broken. And nevertheless, the miracle is that there is a statistical mechanical structure. It's different, you characterize it, you have it, and I finish with this part, and I have almost no time for the other part. So another phase of, here it is, the second part. I think we'll try to go faster, so in order to arrive in time, and says, funny title, Complex Network Perspective of Chaos. And here I didn't take anything out of Google. I just devised the questions for myself. And the questions are, is it possible to represent every single attractor of a dissipative map, like the logistic map, by a network? You must say, well, you really have a lot of spare time if you want to do all that. And then you said, well, how does then the Feigenbaum point look as a network, so that I can look at it as a network? And then another one is more technical, because there is scaling underneath this. Is there a renormalization group transformation that you can apply to these networks? And tells you, I mean, this is more sophisticated because there are fixed points, trivial fixed points, non-trivial fixed points. All these features of is more technical. Then you say, can you assign an entropy to a network? This is, you look at the network, you say, oh, this network has a lot of entropy, or this network has less entropy than this other one. And if you can assign, does the entropy play an important role? And finally, because usually referees ask for the last question, that's why it's there. So this slide is because I thought this is the second part of this meeting has to do, you see, it has no patterning, no segregation, and no differentiation. No, well, if we look for it, they were. If what we have seen some patterning.
It's more chaotic.
Well, anyway, this says nothing. But here is the algorithm. It's an algorithm. An algorithm that is very simple, very enjoyable to work with it, and gives beautiful results. You have time series. You have any time series. And then that's what the link was asking Alvaro. Please tell me about typical time series for social networks. Is where tweets or thinking, or well, in finances, the stock prices, or for electrocardiograms, or for, but anyway, you have any time series. And the method is very simple. It just says, look at the values, say they are real values, in this case are positive, and they don't have to be, of the time series, subsequent values, and just plot them, and look at them as if they were buildings. And then you go on top of the building, and you just look ahead and look behind and see how far can you see. There will be one value of the time series that will stop you from seeing what is ahead because it's got a larger value. So what you say is the algorithm is very simple. Just convert every time into a node for the network. And now you're going to place a link between two nodes if they are visible from each other. And here is a simple example of these values: large, smaller, larger, larger, smaller. And then here is the algorithm applied, and this is the network it produces. It's a little game. And then I take away one of the values, the smallest value, and repeat the algorithm. It gives me something simpler. And keep doing it. And this graph here is because later on, maybe I don't have time today, I'm going to talk about this renormalization group transformation of elimination of nodes and so on. So this is the algorithm. And here are results for the unimodal map. For example, here you have period 2, here is the time series, here you have the graph. Here you have period 4, so you have the time series for period 4, and then here you have the corresponding graph that the algorithm gives you. And then you have, say, fully chaotic time series, which is here, the time series, and here is the graph. And you have here inside period 3, and you have that, and so on. So these are simple results. And then, I don't want to go into detail here because it's also not much to say, just to say that the dynamics of a unimodal maps, which is sometimes it's close to what's called symbolic dynamics, but you don't have to think of symbolic dynamics. The dynamics, it's a deterministic system, so that the order in which positions inside an attractor, a periodic attractor, are visited is fixed. It's a little dance that has to be repeated on and on without variations. And that feature is that allowed for this simple algorithm to give us results, analytical results. I'm not showing much analytical results. Here I'm just showing the cascade. The cascade, this is period 1, period 2, period 4, period blah, blah, blah. And you can see how, you can imagine now, if you continue this process, how it would look for n equal infinity. See, if I take this link away, I recover that. And if I take these two links away, I recover that, and so on and so on. But if I'm already at n equal infinity, now it no longer happens. I am at the non-trivial fixed point, and now it reproduces itself. I cannot get away from it. And you have a self-similar network. And that is what I said. You're looking at the network at the onset of chaos. And now, but because it's so simple, you can work out the degree distribution. And the degree distribution is shown here. It's not a free scale network, it's just it's exponential. And here are results and corroboration, numerical corroboration, and you have the average connectivity or degree. In fact, with this algorithm and these maps, you can only have up to connectivity 4. And so you have those results. And here I'm showing you a sequence of horizontal visibility graphs for the band splitting. Here is 1 band, 2 bands, 4 bands, 8 bands, and you can see that they lose the irregularity and they resemble more and more what we've seen in the previous slide for the periodic attractors. They have to join. They have to join and be the same. You can, I'm just going to mention it, this is just showing the typical self-affine, self-similarity of this. In fact, given the algorithm, the chaotic nature of the network, or the reflection of chaoticity in the network, will only come from the upper band. And the lower bands already acquire periodic features. So when there is 1 band, everything is chaotic. When there are 2 bands, this is chaotic, but this is already regular, and so on and so on. I'm describing it. It's more fun to go with the argument in more detail. And here is, I'm going to be skipping the end because I think I said it was going to be a dessert. And so dessert should not be heavy, tired, so I'm going to be skipping. I'm just not going to describe it unless by public demand I'm asked to do it, and I don't think you will. But this has to do with the renormalization group, it has to do with the fixed points, and there is a non-trivial fixed point at the Feigenbaum point, and there is a trivial fixed point at period 1, and there is another fixed point at fully chaotic attractor, and there are details of how it works and how it is reduced some periodic network finally to the trivial fixed point. And then here are flows that are typical of these things. And then I'm going to go towards the end, and I say, well, okay, we have the degree distribution. If we have the degree distribution, we can use it to define the entropy of the network. This way, it could be different ways, but we just say, yeah, this is the degree distribution, and we just write Shannon type entropy, and this is it. And then here is reproduce a very simple procedure, which is to look at the maximum, at the distribution, the degree distribution for which the entropy is maximum. So we use maximum entropy with Lagrange multipliers. And here it is written, just follow it quickly. It's normalization and average. It's like if you were doing canonical ensemble. And then you realize that the distribution that is followed by the one I showed you before, this one, the one that was calculated, is the maximum entropy distribution. The same thing can be done for the chaotic side. So maximum entropy we want. Because we are now building up at this stage, because we've been looking at the other routes to chaos, and we've been looking at the onset of chaos precisely, and some anomalous and also controversial points. But now we're working out what is the statistical mechanics. There is a statistical mechanics of these networks, not necessarily from the attractors themselves, but there is the horizontal visibility algorithm developed by my colleagues in Madrid. When we're looking at these things, now we are finding out that because there are many contenders of algorithms, methods that would transform time series into networks, and which are the useful ones or not. And this allows for analytical results, but also produces this interesting feature of a statistical mechanical structure. And I'm finishing, well, going towards the end, by saying that actually we found that. Was one of the findings, which is how the entropy of the networks varies with the control parameter. And it's here in black. And here is reproduced, some of you might recognize if you're in the field of simple nonlinear dynamical problems. It's just the Lyapunov exponent of the unimodal map. And then you can put them together and see that there should be a relationship. Not, of course, because there exists what is called the Pessin theorem, which in this case is the Pessin identity, which is very useful. And in these maps, it just says that the only Lyapunov exponent, when it is positive, it is equal to the Kolmogorov-Sinai entropy, which is the rate at which entropy grows in time. But only the positive. Whereas here, here it matches, well, this match. We have now a perfect match because this is mixing apples with pears, because this is the entropy of the network, and this is the Lyapunov exponent of the dynamics. You have to work out which is the Lyapunov exponent for the network, which is not exactly the map. And then they check. And then you can go into a more interesting area, which is the Feigenbaum point. Because of this matching was moving control parameter all over. The last view graph, or many of the things I said before. But I have not talked about what happens at the Feigenbaum point. And there is a new phase there, and the new phase is that you can compare. It's a multifractal in the case of the dynamics, and the algorithm reduces it into a fractal. I don't want to sell to you with more force this result. I would like to, but not now at this time. But there is reason to argue for it. I'd better go towards the conclusions, which are a little bit, not how long am? Oh, 5 minutes, 3 minutes, perfect. And then in the conclusions, I picked up something that I'm very happy that Lee is here, because I put it because of Lee, because I'm going to ask you a question, a very simple one, which is, well, first, over the years, a body of knowledge has been accumulating, and this is a little bit of just saying that last month, a review article of these new phases, not only for the period doubling, but for intermittency, for quasi-periodicity, and other manifestations in complex systems and so on, have appeared. This is for you to, I mean, I announce it. one is interested. And this is the question for Lee, which I found in Google. Says, as a Chinese proverb goes, a sparrow may be small, but it has all the vital organs. Small but complete. It says, the one-dimensional logistic map is just the sparrow of nonlinear sciences. The logistic map, things that they wrote here, like possesses bifurcations, stable, and I mean the attractors and the repellers, periodic windows, ergodicity and mixing, homoclinic connections, chaotic orbits, and so on. And this stops there, but we have added. It's a really very suitable, small, well-defined laboratory to look at things. And it's amazing that still such simple map keeps producing entertainment. But the question for Lee is it a well-known Chinese proverb that a sparrow is small but it's complete? No, I'm kidding. I found it in Google and I thought it was. Now I'm finishing with this old map, which I first used it to tell some community of complex systems fellows that the science of complexity is very old. It's ancient. And then I look first for a very old map. It's very old map. It looks like a flower or like a plant. And then with a good font, try to put certain things on top. It was an old German. Here you have Jerusalem. Here you have the continents, Asia, Europe, Africa. You have America. You have England. Here is the Red Sea. And what this I'm showing to you because it's the way we have proceeded to look at problems in, say, complex systems, which is we take with force a starting point which is nonlinear dynamics. That's in every one of our developments. And that nonlinear dynamics is here the ocean, which is called the chaotic ocean. And then we go into different problems, for example, central limit theorems or different things. And today, of these different possibilities, I chose to talk a little bit about the hierarchies and a viewpoint, the partial viewpoint of networks. Thank you.